All right, looks like we are up and going. Hello, everyone. My name is Mr. Barden. If you've watched some of my videos or been in my classes before, this will look pretty familiar. So I'm pre-recording a few videos, kind of back to back to back, with some different the sound design course at the Denham Springs High School STEM Center. That's what this is. As we're going through this, you may notice there may be some mistakes, or I may stumble a bit. Believe it or not, setting a new class and a new classroom and building a sound booth takes a lot of time. So I don't have the time I normally would have to do a little bit of editing, things of that nature, all of that, setting up the green thing. So I'm just basically live streaming this to no one in my living room, and we're gonna go. Just have these ready to go for these lessons. So again, I'm doing a few of these, kind of one right after the. These are intended for the students in my class, but can be potentially beneficial to anyone. So I'm making them public. Uh, so I'm just gonna jump right into it. This set of slides I've got here is a basic overview about some of the fundamental concepts of sound and the physics involved with that. Now, you don't have to be a physics expert to understand what's going on, but there will be a few numbers and graphs and things like. So let's move my mouse out of the way and just jump right into it, and just answer the question: what is sound? Now, I'm not asking what music is. We'll get to that later, but is essentially the vibration of molecules. So, what that means is we hear something, a sound source causes the molecules in the air to vibrate. These vibrations travel until they are picked up by our ears. Um, excuse me. Uh, Summer allergy season, all the rain, it's knocking all the pollen out of the trees. It's real annoying. Um, these vibrations travel extremely fast, but you'll notice that they travel differently through different mediums. One thing that's relatively kind of tell this too is if you maybe ever swam in a pool, if something makes a noise under the water, you may hear it faster than if you were in the air and heard a noise, or kind of the old movie trope where the person puts their ear to the ground, hears the sound vibrations traveling through that, so they know, oh, there's something miles away that way. It's that kind of idea. It's traveling faster because that medium is denser. Water and ground and denser than air. And because it's denser, the molecules are closer. So they have less distance to travel before they hit each other and transfer that vibrating energy to the next molecule. Uh, In air, that speed is approximately 331 meters per second, or right around 1,000 feet per second. But you'll see, if I bring my mouse back, that that is relatively low. Of this material increases, the speed also increases. Right. So here are these waves, these vibrations I was talking about. So there's going to be force of some kind. In the diagram I have on the screen, that's this gray bar that's vibrating very slowly, but it is vibrating back and forth. This creates, essentially, it pushes the molecules and bunch together, and as they bump into the next one, they bounce off each other. So we kind of get these waves of compression and non-compression called rarefaction. So a lot of density, very spread out. Um, and we see that traveling through the medium. In this case, we can assume it to be air. You can see some of these little red dots are kind of illustrating how the individual are only moving back and forth a bit. It's just the fact that they're bouncing into other molecules that then in turn bounce into the next set and the next and so on, that these vibrations travel through the air, physically pushing the air all the way from me speaking to you listening. I'll put these slides in the description of the video, but I'm not gonna go through it. But this is just another link illustrates this idea in a little bit more of an interactive way, but it's kind of pointless since you can't interact with a YouTube video. But check out this link. Again, I'll have these slides in the description for you. All right, frequency and so again, we've determined that these waves are happening, and that makes a sound. Um, the amount of waves kind of determines the pitch. So let's say you have a microphone or something, and you're able to kind of measure how many of these sound pressure cycles, these waves of energy, are hitting that one point. That number is called the frequency, and the number of cycles per second of the waves is measured in hertz. That's the measurement there. And speaking broadly, higher the frequency, the more hertz in a sound, the higher the perceived pitch is. Um, and again, I'll have these little links here to check out some kind of interactive ways. This on the screen is the same as on the last slide. Definitely recommend checking those out and just experimenting and seeing as we go. Um, so humans hear these differences in hertz exponentially. So every time an octave difference is heard, the frequency of that sound has doubled. So let's say someone played, the C4 on the on a piano, almost like computer, and then C5, we would have doubled in frequency between the lower and higher notes. All right. So here's some of this again, a bit of a diagram here. We've just the standard up here, just normal air pressure. It's kind of no real difference. But then we've got the waves here. You'll notice they get farther apart and close. They've bunched up and they're hitting each other and they're bouncing back to their position. So we get the compression and rarefaction. On the next slide, when we start looking at these more, we'll look at these in what's called the waveform diagram. And what we have down here on part C of this graph. So basically, the way we can look at this is that when the waves are all bunched up together, we've got a really high value graph, and when they're really spread out, we get the low value. And 0, if this line was just a straight line, it would look like it does up top. So again, the higher up on the graph, the more dense the molecules are, the farther they are apart. That's how you can read through some of this. What I have here is just a chart kind of correlating this to musical pitch, specifically on a piano. Look here, this is the frequency, again, the hertz of every note. So let's say we got, here's that C4 I mentioned. C4, we move across, we see there's the note on the piano. It's 201.6 hertz. That's the frequency to create that pitch. To move up to C5, we double that, we get the 523.25. That's the one we want right there. So you can kind of see that as we go, start off at 27.5 on the very lowest note of the piano, all the way up to 4,186 on the highest note, is again increasing exponentially. All right. So the amplitude and the volume. So again, if the pitch is determined by the amount of wave, whatever is determining the pitch, the microphone, your ears, the whatever, the amount of waves, the volume, again, broadly speaking, is determined by the size of the wave. So louder sound is going to be having much more energy generating the waves. It's going to be pushing the air more drastically. Larger waves, larger sound. That's the general way to think about it. Another way to think about it is, if I'm whispering like this, it's going to be pushing the air very, very slightly, and it's very quiet. As opposed to if I'm talking a little bit more loudly. Sorry, again, allergies. I'll be pushing more air as I'm talking, more energy, louder waves, louder sounds. I'm going to dial it back just a hair. Um, represent this in decibels, dB of air pressure, because again, the more air pressure, the louder the sound. Here's a diagram just kind of illustrating what I just talked about. So again, the height of the peaks on these waves responds to the volume. The amount of the waves themselves is the pitch. It's a way to look at it. All right. I'm just going to talk a little bit about how it work, just real briefly. Um, so it's a complex uh, collection of body parts. This thing on the outside of your head is not all of your ear. It's just a part of it. Here is called the pinna, and it's essentially a satellite dish for sound. As these waves travel through the air, um, they eventually will bump into your ears here and get funneled into the inner ear, which is all in your skull. If it's ever not, you've got a problem. Um, so these waves travel through, into your ear and bump into the eardrum, tympanic membrane, if you've ever heard that or taken a biology class. And that causes that to then vibrate. Um, connected to this membrane are three small bones, and they help this sound into the cochlea, a specific organ in the inner ear, way in your head. And what this does is it essentially filters out vibrations. So different parts will respond to different frequencies. So lower sounds get picked up on one end, higher sounds get picked up on the other end, and um, depending on what part of it gets stimulated, it is that different. The signal, it's an electrical signal through different nerves to your brain, and then your brain can interpret the pitch. So different nerves getting stimulated will tell your brain, "Hey, this is a high note. Hey, this." If it's happening a lot, your brain knows it's loud versus it's a quiet sound. I've got the diagram of the ear here, so we can see. Here's the pinna, the outer ear moves in, bounces again this membrane. Against this membrane, the sound travels through the bones, and then to the snail-looking organ, the cochlea, and then again throughout, actually a bunch of fluid and uh, I'm gonna say hairs. They technically aren't hairs like grow on your head, but they're hair-like membranes. And as they vibrate, they stimulate different nerves. That's what these yellow things. Um, and that gets sent to your brain, and your brain figures out what's going on from there. All right, the human hearing range. Um, generally speaking, humans can hear sounds from between 20 hertz and hertz. This varies from person to person depending on the age, the shape of their ears, the quality of the speakers, how far they are from the speaker. It's a very, very variable range. Um, Generally speaking, most people can hear about 20 to 20,000 hertz. Remember, the piano started at about 27 and ended right around 5,000. Um, so again, we can hear much higher than that. But as it starts getting really high, it gets harder to pick out pitches. All right. In terms of volume, we can generally hear between um, 0 to 100 decibels comfortably. Sounds louder than that can cause pain and hearing damage. Um, and listening to moderately loud and loud sounds for long periods of time can also cause that same damage. That's why a lot of devices will tell you turn the volume down or take a break from listening from your headphones because you can permanently damage your hearing if you're not careful. um, right, and again, each person's specific response to a volume is unique with sound volume or sound frequency. This here is just a diagram kind of illustrating what I just mentioned about um, sound volume. So again, these are all up, but kind of this, 80 down this green area, that's basically fine. No risk. And it shows some of the approximate sound volumes of, some pretty common things. Into this kind of yellow range where you could run into some problems. And then as it starts getting up into these higher range, you can start, potentially hurting your ears, causing, if you're, you know, too close to the sound and you listen to it for too long, um, you don't want that to happen. All right. I'm not going to go through this on video, but I do have a link to another video in these slides. Come on. 15, there we go. And basically it just goes through um, the full 20 to 20,000 hertz so you can kind of see where yours are. I recommend not listening to it on headphones because it can get a little grating in certain areas, but just on some decent speakers if you have those. One thing is basically that humans can hear different sounds at different volumes. And I've just got a diagram showing that, let's say you had this is a really interpret graph if you've never seen it before, but basically, um, as a sound travels through here, it's, it'll be, even though it starts at a specific sound volume, it may be perceived lower bit. So you notice that generally it kind of gets quieter. There's a bump right around here, which is where a lot of people's speaking voices will sometimes lay. So dip, and then it picks towards the end. That's very broadly, but the important thing to know is that if I had a sound that I played at a constant level and the pitch changed drastically, it may sound like the volume is changing. You may have to adjust that slightly. All right, ways to look at sound. So we can represent sound a bunch of different ways. We've done it a few ways already here today, and I'm just going to go through some of the more common ones that we'll see. The first one is musical notation. Um, then this class will be starting with some basic music theory, so we'll get really familiar with this kind of thing. But basically, your clef of music that tells you, what each line or space is, and then as you place a note on each line or space, that's telling it to play the note. And if I'm not going to do it right now, but if I went back and there was that big vertical chart, you'll see how that note corresponds to a specific frequency. All right. On a keyboard, these notes, again, it's laid out same kind of thing. So again, we got the C, D, E, F, G, A. It's all right there, but it's just horizontally laid out, so you can play it, like this, as opposed to vertically in spaces up here. So again, that's basically that. Octaves. So I mentioned before that each octaves is a doubling of. So here I've got A3 is 220 hertz. So if you played this note on the keyboard, it was tuned properly, it would play a sound that was at 220 hertz. If I went up and played A here, it would play a sound at 440. And then at A5 would be 880, and so on and so forth. So it's just something to keep in mind. We've already looked at these just a little bit, but again, this is just saying that, again, you have the amplitude of the sound being represented vertically and the, over time. So in a digital audio workstations, you'll get something like this, where it's, moving very quickly, but as you zoom in, you'll get something like this, where you can see that the amplitude picks up and changes over time. In a lot on this bright blue one, you get something like we have over here. And again, the higher on the graph is the higher pressure, where all the molecules are closer together. The lower values, they're farther apart. So I got there. It's just one continuous line to represent the sound. Here's this diagram again, just to illustrate that. High pressure, high point on the graph. One whole wavelength of the wave. spectrograms. So this shows the frequencies given in a present sound. There can be multiple frequencies in a sound, and basically it's just the brighter, the more present that frequency is. So we can see down here we've got um, a bunch of these lower frequencies, but then there's also a few higher, quieter frequencies present in the sound. We'll talk about overtones in a little bit, but that's basically what's happening. And that's actually the end of these slides. So I guess I will talk about overtones just a little bit, just to wrap out today. So basically, what an overtone or a harmonic, you play a note, there are additional other notes that are happening at the same time. That may seem a little weird, but the way it works out, main pitch. Let's say this right here is our note. Um, every one of the lines here is essentially a multiple, a whole integer multiple of that same frequency. You played a sound at 100 hertz. The next harmonic would be 200 hertz, 300 hertz, 400 hertz, 500 hertz, and so on and so forth. It's that one's really easy to calculate, and that's naturally going to occur in the sounds. Where we get unique sounds and what's called timbre, and why instruments sound different than one another, is the fact that unique sound has a different combination of these in different volumes. You'll see that this particular sound has these kind of 3 or 4 lines are the brightest. And we get kind of a darker, and here before some of them start picking up again. Um, let's just say hypothetically this was a flute. I don't know for sure actually. Um, a clarinet or a guitar or a piano, cello, something would have a different combination of these lines. All right, so maybe there's a more of a gap here, or it plays you see every other one, or it really cuts out the whole top. It varies, and everything that makes sound has a different combination of these overtones that we can see very clearly in a spectrogram that give it its unique characteristics or its unique. And that's basically it. Again, it's all the natural harmonics are uh, whole number multiples of that original fundamental. If you play a sound of 100 hertz, the next, let's pretend that's this bottom line here where my mouse is. The next one will be 200 hertz, and then 300, 400, 5, 6, 7, 8, 9, 1,000 hertz. They just would be brighter in different combinations. All right, that's going to wrap it out for this one. Like I mentioned, I'll stick these slides in the video description, so if anyone checking these out can. And it's going to do it for this one. So I will see you all.